Hello, everyone. I'm glad to see all of you. Welcome to the COSIC Seminar, where I'm going to present the paper called CovFUZZ, the coverage-based fuzzer for 4G and 5G protocols that was accepted to the Euro SMP conference this year. But to set the scene, actually, I'll start by giving a general introduction to fuzzing, because I guess not many people know much about fuzzing. So I'll give you a general introduction, explain what is fuzzing, what are different classifications of the fuzzers, and then give you a concrete example using the AFL fuzzer, the most well-known fuzzer out there. And then the second part of my talk, I would cover the paper itself. So the total length of the presentation should be around 40 minutes, and then we'll have some time for the questions. So let's start from introduction to fuzzing. So what is fuzzing? So fuzzing is the way how to test the program in the automated way using sending different kind of inputs, which can be invalid, unexpected, or random to the computer program. And by the computer program, I mean anything that takes any kind of inputs. It can be the IoT device, it can be the mobile phone, it can be the software that is running on your laptop. It can be anything. So, and the idea is to have the fuzzer, and then the fuzzer will send different inputs to the system under test. So in this presentation, I'll refer to this computer program as a system under test. And then the fuzzer will get some kind of feedback observing the behavior of the system under test. And the idea is to use the fuzzing to find out the anomalies in the behavior of the system under test. So just to give you a quick example, so here let's say we send the first input, we get no anomalies. We send the second input, we again get no anomalies. And then after some time we send an input n, let's say, and we get an anomaly. In this case, the system under test has crashed. So this is definitely an unexpected behavior. And this is what the fuzzer aims to find during the fuzzing process, basically. So already on this picture, we can see actually two main challenges of fuzzing. So the first challenge is, how to intelligently generate the inputs. Because you can imagine if you just send some random inputs to some computer program, it's not likely that it will crash. So it's very important how the fuzzer generates these inputs, what kind of techniques does it use to do that. And the second is what feedback can we use from the system under test to first improve the generation process of the input, and secondly, to reliably detect the unexpected behavior of the system under test. So this is like a big picture of the fuzzing and its main challenges. So now I'll give you a quick classification of fuzzers. So first, we'll start from the classification that tells how much does the fuzzer know about the system under test. So the first type of fuzzers is so-called black box fuzzers. They have no access to the system under test code. They cannot instrument the code. And basically, all they do, they generate inputs without observing the internal state of the system under test. So this kind of fuzzers typically are used when you don't have a direct access to the source code. For instance, in case of embedded devices, that can easily happen. Then the second category is completely the opposite. It's called white box fuzzing. So there you have the full access to the system under test code. Typically, the fuzzers that are white box fuzzers, they're relying heavily on the code analysis, on so-called symbolic execution or constraint solving methods. And they generate the inputs via using these heavy code analysis techniques. And of course, these kind of fuzzers are much more efficient, but they also require a lot of time to really generate those inputs to solve these hard problems, basically. So this type of fuzzers typically are used only in the critical sections of the code, where you really need to make sure that you don't have any security vulnerabilities. But the most well-known type of fuzzers is something in the middle, which is called the gray box fuzzers. So there you have a kind of partial access to the source code of the system under test. By partial, I mean you don't really do any heavy code analysis, but basically you only add some instrumentation during the build process. So for instance, you can add the code coverage instrumentation to fetch the information about the code coverage during the fuzzing process, or you can instrument it using the address sanitizer, memory sanitizer, to make it easier for you to figure out when the memory vulnerability happens. And then in general, these fuzzers, they're using the code coverage feedback to guide their generation of the inputs. We're gonna see an example of that soon. And yeah, this type of fuzzers are the most well-known fuzzers. They're general purposed for the security testing. And yeah, if you're gonna encounter some fuzzer out there, then probably it would be a gray box fuzzer. So the second classification I want to give you is regarding the input generation. So there are two types of fuzzers. One is called mutation-based fuzzer. So basically all it does, it mutates the inputs. So first, it expects the user to give a seed corpus, let's say the first input, that it can use as a seed for the future mutations. And then it starts mutating this input to get new inputs. Again, we're gonna see an example soon. So this type of fuzzing, it's a bit less efficient, but it requires almost no prior knowledge about the format that the system under test expects to get. And the most well-known fuzzer AFL is actually the mutation-based fuzzer. So the second type of fuzzers is called the generation-based fuzzer. So the idea of the generation-based fuzzer is to generate the input seeds from the grammar. So not from the previous seeds, but from the grammar. And yeah, as you can imagine, not for all the programs, not for all the systems under test exist grammars that they expect to get. And therefore, if you use the generation-based fuzzer, you need to either manually construct this grammar, which might be very hard or sometimes even infeasible thing to do, or find already existing grammar that you can use during the fuzzing. And the generation-based fuzzing is very good for the structured data. So for example, for the protocols, like yeah, any kind of protocols, but they are, of course, much harder to make work. So you really have to know a lot of things about the protocol or find an existing grammar, as I said. So now I'll give you an example of the most well-known fuzzer, American Fuzzy Lob, which is named after this cute creature. And this is the most well-known fuzzer, the so-called holy grail of fuzzing. It was released in 2013. It's a gray box software fuzzer. So by software fuzzer, I mean that both the fuzzer and the system under test, they should run on the same machine. And it's a gray box as it adds some instrumentation, code coverage instrumentation during the build process of the system under test, and then uses the code coverage as a feedback during the fuzzing. Also, it's a mutation-based fuzzer, so it expects you to give some kind of initial seed, and then it starts mutating it further and further. The AFL is not maintained since 2020, but there is a community-supported fork of AFL called AFL++ that is alive and thriving nowadays. So now I'll give you an example of the program and explain you how AFL would handle this program. So in this program, we see it's a C++ program. It expects the user to provide an input and then performs a lot of checks. And then eventually, if the input is equal to COSIC, then it will crash. So assert false will cause a crash of the program. So this way, we can imitate the crash in the kind of real program. So the question is, how will AFL++ approach it? And will it be able to find the crash or not? So the first thing that you have to do, you have to provide the AFL an input seed. Because it's a mutation-based fuzzer, it has to start from something, and that something should be provided by the user. So in this case, I provided the string ESAT as an input to the fuzzer. So then the first thing that fuzzer does, it executes the program using this input. And it gets some kind of a baseline of the code coverage using this input. So as we can see, if you feed the input ESAT to the program, then, okay, this will be executed, but the line 13, this check will not pass, because the length is only 4, not 5. And therefore, we will not get to the line 14. We'll jump to the line 25, and then the program will end the execution. So this code coverage would be like a baseline for the fuzzer. Okay, so then the fuzzer starts doing its job, starts mutating the inputs. So the first mutation that happened in my case when I was running the AFL++ was this input. So fuzzer from ESAT created during the random mutation, using the random mutations, it created this string. You might ask, how did it happen? So let's see in more details, how did it happen? So what is happening internally in AFL++? AFL++ is using some simple mutations stacked on top of each other. So let's see how it happened exactly. So first of all, we imagine the string as a byte sequence, like we are the computer basically. And then the first mutation that AFL applied is inserting the random byte at offset 0, so basically in the beginning. And now we get the question mark ESAT already. Then AFL adds a random value on offset 1, and we get this string. Then we insert the random byte, we get this string, and finally AFL flips least significant bit on offset 3, and then we get finally our input that we see here. So as you can see, all the mutations are quite simple, and they are stacked on top of each other. So this is the way how AFL comes up from a seed or from the previous input with a new inputs. Yeah, this type of mutations, of course, those are the part of AFL, but this is not everything that AFL has. It also has like byte flips, subtractions, insertion, deletion as well, and some other things which you can explore on AFL++ website. They have quite a nice documentation there. But this is basically the idea how the random mutations work. So and then after getting this string, this input is fed to the program, and AFL observes if new coverage was found or not. So in this case, it was not found, because again, the input doesn't have a length of 5. So then the AFL++ tries a new input. Again, no new coverage. Then tries a new input. And then finally, at some moment, it will find an input which has a length 5. So we see that the check on the line 13 is passed. So we are getting through and into the line 14. But the line 14 now, again, doesn't pass. But regardless, this input led to the new coverage. Yeah? And because this input led to the new coverage, it is being saved in the queue as a promising input. So now in the queue, we'll have two inputs. Yeah, one original seed and one new input that was generated from this original input. And then the algorithm basically continues. But now we have two seeds kind of that AFL++ can use. So let's say first tries to use the second seed, get some new input, again, no new coverage. Again, new input, no new coverage. Then it might switch at some moment and generate an input from this. And in this case, we got new coverage, yeah, on the line 15. So basically line 14, the check has been passed because the first letter is C. And we got new coverage. I think you got the idea. So now this input is again saved as a promising input in the queue, and it continues, etc., etc. After some time, AFL++ will figure out how to get even further in the code. And then eventually, this way, we're gonna get the input COSIC that crashes our program. So that's the overall idea of how the mutation-based fuzzer that uses the coverage as a feedback works. You might ask, how long did it take for the fuzzer to create the input COSIC from the initial seed E set? And here are some numbers. So the first column shows the number of executions prior to this input, and the second shows the timing. So as you can see, in the beginning we have 0, and then towards the crash seed, we see that this crash seed was number 1,116, so around 1,800 inputs were tried before that, and it took only 3.6 seconds. So the throughput of the fuzzer, at least on my laptop, it was around 5,000 inputs per second. Yeah, and this is how much did it take for the fuzzer to find the crash using the coverage feedback. You can imagine if it was a random fuzzer, then it basically had to brute force 5-letter word, and then it would take much, much, much more time for that. All right, so that was basically a quick introduction to the fuzzing classification, and a quick example for you of how AFL++ works. So now we're gonna move on, and before discussing the fuzzer for 4G and 5G systems, I wanna give you a very quick introduction to the 4G and 5G, just 2 slides. First, the 4G and 5G protocol stack and the architecture in general. So in 4G and 5G, we have 3 main instances in the architecture. One is called the user equipment, which is basically your phone. Second is called the base station, which is responsible for handling the radio communication with your phone. And the third is called the core network, which is basically a brain of the whole network. And amongst other things, it contains information about users, keys, etc. The communication between the phone and the base station is called uplink, because basically it goes from your phone up to the base station. And other way around, it's called the downlink communication. And as vast majority of network protocols, it has its own protocol stack, starting from the NAS layer on the top, finishing with the layer 1 or the physical layer on the bottom. And when, let's say, the UE, the user equipment, starts or wants to send the packet to the base station, then the packet gets generated first of all on the top layer, then it goes down, 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 getting more and more layers like an onion, and then is being sent on the physical layer to the base station, where it gets parsed in the opposite direction. And another thing that I want you to talk to you about is what is called the attach procedure. Here an example of the 4G attach procedure, but for 5G it's very, very similar. So the attach procedure is the first thing that happens when you boot your phone, when it tries to connect to the network. And then in the end of attach procedure, you can finally use the internet connection. So here, as you can see, the attach procedure contains a lot of messages, a lot of communication back and forth. For this presentation, it's not so important what is happening in this communication. Just remember this picture, and it will be important towards the end. And the packets in bold here, those are being fuzzed by the framework, by my framework. The framework would be fuzzing in both directions, in uplink direction and in the downlink direction, so in different modes, basically it can work. When we talk about fuzzing downlink, then only the messages that are going from the base station to the UE would be fuzzed. And when we're talking about fuzzing uplink, then other messages that go from the UE to the base station will be fuzzed. Okay, now I think we're ready to start discussing the paper, which is called CovFUZZ, Coverage-Based Fuzzer for 4G and 5G Protocols. So first of all, what are the main challenges when fuzzing protocols, when fuzzing phones, like embedded devices? So let's see. So first of all, protocols are stateful. It means that the system under test will expect the certain packets in certain states at certain times. And the stateful fuzzing is something that is not very widely supported in the fuzzers. So it's much harder to find the stateful fuzzer than just a normal fuzzer. Second thing is that the protocol packets are typically very highly structured. And if you break the structure, then most likely your input would be rejected by the system under test, which will lead to inefficient fuzzing. Another problem is the presence of encryption or integrity protection, or sometimes the liveness detection using the challenge response mechanism. And there, if you will violate encryption or integrity protection or send a wrong response to the challenge, then again, your packet would be rejected without penetrating deeply into the code. So this is, again, something that you, as a creator of the fuzzer, should think about. And finally, fuzzing the embedded devices has the following challenge, is that the embedded devices, they lack feedback. So basically, they're kind of a black box from where you can hardly extract any information about the code, about the code coverage, for example, that is widely used in different fuzzers. And also, it's much harder to detect the memory bugs, because typically this code is not instrumented with the memory sanitizers. And some of the memory violations, they are not, they do not cause the crash at all of the program. Or sometimes they can cause the crash that will happen after some time, and it's hard to figure out why did it happen. So the goals of the work that I'm presenting is to present a fuzzing framework for testing 4G and 5G protocol implementations. And during this work, I've came up with a novel coverage-based algorithm to be used in the gray box settings. So in the gray box settings, when you can fetch the coverage from the system under test. This can be applicable, for instance, for the device manufacturers who have this information during the manufacturing process. And also it can be applied when you are trying to fuzz, let's say, the open source instances, open source libraries that implement the 4G and 5G stack. But then I also kind of present the novel way how to guide the fuzzing even in the black box scenario, where you don't have a direct information about the code coverage from the system under test. And then finally, I evaluate the fuzzing framework using first open source implementations to evaluate the gray box part, and also using the real devices, the commercial off-the-shelf phones and modems to evaluate it in the black box scenario. So now let's see the architecture of the framework. So the architecture, yeah, it's quite a big slide. So let me go step by step here. So first, let's focus on the left part here. So left part is using the existing open source libraries, such as srsRAN and Open5GS. And these libraries basically implement an open source version of the core network of the base station and of the UE as well. So you can basically build a local 5G and 4G network on your laptop. And these open source libraries are very helpful because they can generate the benign 4G and 5G packets. And you can even connect your own personal phone to these open source networks. So they can send the benign packets to the system under test. But of course, during the fuzzing, we don't want to send the benign packets. We want to fuzz them, we want to mutate them. And that's why this part on the right exists. So after the benign packets get generated, we intercept it, and we have a possibility to intercept it on two layers. One is RRC and one is MAC. Why do we do that? Because on the PDCP layer, we have an encryption. So if we intercept the packet only on the MAC layer, then we cannot change anything that was done before the encryption, because it will violate the encryption and the packet will be rejected. That's why we need the interception point on the RRC layer, so we can mutate both the RRC layer fields and the NAS layer fields at this point. And then on the MAC layer, we can mutate the fields below that. And now I'll show you a small animation of what happens when the packet gets intercepted. So first of all, let's say this open source implementation generates a packet, which is then intercepted on the RRC layer, and is being sent via the shared memory interface to the fuzzer, basically. So the first thing that fuzzer will do, it will dissect the packet. So it will get the information about the fields in the packet and about the type of the packet. Basically similar to how Wireshark does it. Then, once we have this information, we can mutate the packet more intelligently. And here we have two strategies. One is called replay, changing the whole packet for some old packet. And the second is called the mutation, where we want to change only the certain values, certain fields in the packet. So in this case, we choose randomly the mutation, and we mutated at random the middle byte. So it was 0, and now it's 11. And now this mutated packet is sent back via the shared memory, again to the interception point. In the meantime, we save this packet for the future use for the replay. And then this packet gets propagated to the physical layer, it gets information from the other layers, like an onion, and then it is sent to the system under test. So this is basically what happens with every packet that goes from the base station to the system under test. And one fuzzing iteration, it contains from multiple such packets, so basically from the packets that are in one attached procedure. And after the fuzzing iteration has been finished, then the coordinator performs a couple of checks. So first of all, it checks whether the system under test is alive. If it's not alive, then something unexpected happened, probably a crash in the system under test, and we save the seed that caused the crash for the future investigation. And restarts the system under test if it, again, has been crashed. Then it checks whether the protocol stack implementation is alive. Yeah, it can be also helpful. Protocol stack is also, it can crash during the fuzzing easily. And then it gets the information about the coverage. Yeah, so in this case, if possible, it gets the information about the coverage from system under test. If it's a phone or if it's a real modem, then it's not possible. Then we don't do this step. But we always get the information about the coverage from the protocol stack implementation. And actually, this coverage information can be used to approximate the coverage from the system under test. Because if you think about it, they always have constant communication between each other. And then the code that is triggered in the protocol stack implementation, it impacts the code that is triggered in the system under test. And this is the idea that we're gonna use when fuzzing black box. So we're gonna rely not on this coverage information directly from the system under test, but instead we're gonna rely on the coverage information from the protocol stack implementation, namely the base station. And then finally, to trigger the new fuzzing iteration, the coordinator sends the command to the system under test to again try to connect to our network. So yeah, this is basically how the whole fuzzing framework works. Now a couple of details that I want to mention. So first of all, how do we choose which fields to mutate? So initially, every field in the intercepted packet gets a probability of being mutated. So, and this probability is uniformed and is kind of fixed using this k hyperparameter, which basically tells you the average number of fields that will be mutated in a packet. Yeah, and here the FP is just the total number of packets, total number of fields in the packet. Here, just to give you a quick example, so let's say if the k is 1, and we intercepted this packet that we just saw, which has 3 fields, then each field will be assigned the mutation probability of 1/3. And then, when we want to mutate these fields, we just iterate through all the fields one by one, and mutate the field f with the probability that is assigned to this field. So in average, let's say in this packet, there will be 1 field mutated every time. And by mutate the field, I mean just set the random value to the field. And then I have 2 fuzzers that I've implemented. One is called the random fuzzer. Basically, this is you can think about it as a baseline strategy, where the mutation probabilities are fixed from the start of the fuzzing and throughout the whole fuzzing campaign. So they're fixed and characterized by this parameter k, as we just saw, but they never change throughout the fuzzing. And then the second fuzzer is called the coverage-based fuzzer, which is kind of the main point of the work. So it aims to maximize the coverage of the system under test. How does it do that? It dynamically adjusts the probabilities after every iteration. So if the new coverage was found, then it increases the probabilities of the fields that were mutated during this iteration, saying that those fields are promising and they lead to the new coverage. And if the new coverage was not found, then these probabilities get decreased. And the size of this increase or decrease is controlled by the parameter beta. I'm not giving you here the full formula, but you can check it in the paper. But the logic of this change in the probabilities also takes into account the total number of fuzzed fields in the current iteration, because we cannot really say precisely which mutation caused the new coverage. Let's say we made 10 mutations, we are not sure what caused this new coverage. So we always scale this increase by the total number of fields. And then the second is the current fuzzing iteration number. So the logic here is that finding the new coverage in the beginning is much easier than towards the end of the fuzzing. Because in the beginning, you have very little code explored in the system under test, and you will very often get new coverage, regardless of what you're doing pretty much. And therefore, in the beginning, this increase is much smaller than towards the end. And then I've run experiments in two modes, as I already mentioned. One is the gray box mode, when the coverage we get directly from the system under test. And the other one is a black box, where we kind of approximate this coverage using the coverage from the protocol implementation, open source protocol implementation, namely the base station. And now I'll share with you some results. So first of all, the tests on the open source implementation of 4G. So initial experiments were run to determine good parameters k and beta, because those are the hyperparameters in my framework. So I had to run a lot of experiments to determine good values for different fuzzers. And then I ran 24 hours experiments with the best parameters, with the random fuzzer, with the coverage-based gray box fuzzer, and the coverage-based black box fuzzer. And here you also see the baseline, what happens if there is absolutely no fuzzing. And you can see that the best performing fuzzer was the coverage-based gray box, which is logical because there you extract the coverage information directly from the system under test. Then the black box fuzzer was in the middle, was the average. There we still use some coverage information, but we kind of approximate it from the protocol stack implementation. And then the random fuzzer performs the worst. Yeah, it doesn't really take into account any feedback. It uses the constant mutation probabilities. And then during this fuzzing, I also found the 7 vulnerabilities in the open source 4G stack implementation, which were 6 crashes, 1 hang, and 4 of them were buffer overflows. So then I ran the experiments using the real devices, the real commercial off-the-shelf devices, and those are the results. So all of them were tested in a black box fuzzing scenario because we cannot get the coverage directly from the system under test in this case. It was around 70 hours experiment per the device, and in total we found crashes in 10 out of 13 devices that we tested. And interestingly enough, 5 out of 6 5G devices were vulnerable using the 4G attach procedure, during the 4G attach procedure. The crash reasons are mostly unknown because typically these modems or the phones, they do not expose the information about why this or that crash occurred, and it requires probably reverse engineering to determine the precise cause of the crash. So now, in the end of my presentation, I want to show you a small demo of simulation-based fuzzing. So basically fuzzing on one laptop using the open source instances. Let me try to Yeah, so what is going to happen? So here we see the screen with the fuzzer, and the fuzzer already knows the seed that causes a crash. This is just used to replicate basically the crash. And the fuzzer will start 3 instances: the UE, the base station, and the evolved packet core. So the 3 instances that we discussed when discussing the 4G and 5G architecture. So here we see that 3 instances has been started. So this is the UE, this is the base station, and this is the core network. And in this demo, you'll see the core network crashing after the UE sends a malicious packet via the base station to the core network. So keep an eye on the core network, it will crash shortly. Yeah, so it crashed, and here we see the reason. Yeah, I'll read it for you. It's the address sanitizer tells us that it was a heap used after free vulnerability, and it was located in the handle identity response function. So let's remember the attach procedure that I shown you before. So here we're not gonna focus on the whole procedure, we're gonna focus only on this part where our interesting packet happens. So here first, in the benign version of the attach procedure, identity request is sent to the UE, then UE responses with the identity response, and then authentication request is sent and authentication response is received. So what does UE do in order to trigger the crash? It's very simple. Instead of sending the benign authentication request here, it just replays the identity response message basically a second time here. And it's enough to cause the use after free vulnerability in the packet core, which is, of course, is an unexpected behavior. All right, so in conclusion, some takeaways from my presentation. So first of all, everything that takes some kind of inputs can be fuzzed. And the choice of the fuzzer, it depends on the availability of the source code of the system under test, as well as the type of inputs the system under test expects to get. Fuzzing stateful protocols is tricky because there the timing of the send packet matters. Also, you have to solve the issue with the encryption and the integrity protection. Fuzzing the embedded device is even trickier because there you not only have these problems, but also you have the lack of the coverage feedback and lack of the code instrumentation. It's hard to find the figure out when the crash happened. And the CovFUZZ is the paper that tried to address these issues and also propose the coverage-based framework for fuzzing 4G and 5G devices. It proposed a novel coverage-based algorithm that can be used in gray and black box scenarios, and it is kind of supported by the experiments where we found 10 devices vulnerable out of the 13 that we tested, and 7 vulnerabilities in the open source 4G stack implementation. Thank you very much. Now I'll be happy to address your questions.